will say something. All right, good morning, welcome. For those of you who are here in person, for those of you who are online. It's a real pleasure to welcome Stefan Fuglistaller.
Perfect.
Thank you. He first studied tectonic science, right? I guess geophysics for his master's, and then he did a PhD on polar stratospheric clouds in 2002. I think he went to University of Washington, then Cambridge for a couple of years, and then he is on the faculty of Princeton since 2010. And he is not only the director since 2015 of the program on atmospheric and oceanic sciences, which is the sort of the PhD program that is done jointly with GFDL, right? GFDL plays a big role, but he's also now the director of the NOAA Cooperative Center in, what is it? Institute for Modeling the Earth System. And with that, he has a lot of official postdocs because of NOAA bureaucracy, but that's a different story that won't be discussed here. Today we have a pleasure of having him telling everything we need to know about radiative thermodynamic modes of climate. So welcome, Stefan.
Thank you very much, Joao, for the introduction, and thank you very much for the invitation to give this seminar here. Quick question, can you hear my voice? Everything is good? Okay, wonderful. So I will talk about what we might call radiative thermodynamic modes of climate. And I would like to start my talk with a few sort of motivation slides. This is a picture of Suki Manabe, which you probably all know, recipient of 2021 Physics Nobel Prize from GFDL and the AOS program in Princeton. And his seminal contribution was sort of starting with more or less this figure, which is a calculation of radiative convective equilibrium of a sort of a column with a surface condition of the ground. And the point here is that when he did that calculation and he assumed that relative humidity would be sort of roughly the global average relative humidity, he obtained a solution that is remarkable in several ways. First, it gives you roughly the correct average surface temperature for the globe, which is quite remarkable if you think about the wide diversity of climates that we have. So you can all average into sort of one single column, and the average solution corresponds to the average over the planet. And the second thing was that when he assumed that relative humidity was constant, with this single column, he could basically anticipate already climate sensitivity to a very good degree, except, of course, clouds, right? This solution is not able to have a predictive solution for clouds. But for the clear sky part, this gives you a very good estimator. This is really remarkable if you think that water vapor, or just water, the phase transition is such a nonlinear process that somehow, in the end, if you average it all, it seems to be pretty linear. The same is true. This is from a figure from Jonathan Gregory's paper. If you perturb a climate model at some time point T0, radiative top of atmosphere perturbation, the system goes back to equilibrium. If you plot the temperature change on the x-axis as function of the top of atmosphere imbalance, it's a radiative budget, it's to good approximation linear. We note there's a bit of scatter, but again, it's quite remarkable that in principle everything turns out to be very linear. Part of that is giving us pause for thought when we look at the more recent record, when we run a climate model, for example, with observed sea surface temperatures, we observe a cloud radiative shortwave feedback that looks like this. So each point here corresponds to an average temperature and the corresponding global average shortwave cloud radiative effect. And this is over the historical period, so since the late 1870s to present. And what you see is first there is scatter. So it's not a single sort of functional form between average temperature and shortwave CRE. But you can ask, is that now a big scatter or is it a small scatter? And one of the problems that we have is we don't really have a theory that would tell us what is the expected range of variation. But certainly what catches your eye more is that for some part, it seems to be a positive correlation, and then for other points, it's negative. And if you ask what is different of this versus this, then it is the post-79 period. So there seems to something have happened that the cloud radiative feedback got from a positive to a negative in the short wave. this is clearly not what you would get if you had a single column, right? Kind of where everything is sort of more or less a monotonic function of surface temperature. Okay, so just briefly, kind of why is it actually remarkably linear? A lot of things hinges in the end on the spectral properties of the water vapor molecule, and other greenhouse molecules, CO2 is the same, whereby the mass absorption spectrum looks something like this if you plot it against sort of wave number, for example. If you look, the orange line here is the Planck spectrum. If you look sort of where you actually have power and you weight the mass absorption coefficient with the power that you have there, that gives you sort of how relevant a given mass absorption coefficient is. It looks something like this. If you sort that, and you have all the high absorption coefficients here and the low ones here, and you see this is a logarithmic scale, so it's an exponential decay. If you multiply that with sort of a certain amount of mass and neglect for the moment all the complications with broadening, pressure dependent, etc., but roughly what it gives you is a corresponding picture for the optical depth, and that means sort of your optical depth scales basically logarithmically if you ask what is the fraction that I have from outgoing long wave radiation from the ground versus from the atmosphere. And because water vapor is exponential, that means actually it is then more or less linear in temperature. And the result is that sort of the repartitioning of emission to space from the ground versus the atmosphere is roughly linear with surface temperature, which explains a lot of sort of these feedback parameters, but it also tells you something about the hydrological cycle, because the atmospheric emission to space, this is the cooling to space approximation, valid in the RCE case, is roughly equivalent to atmospheric radiative cooling, which is compensated by the latent heat release that we have, right? So this is a lot of it, kind of why you can do these things in a linear way, is hinging on the spectral properties of the greenhouse gases. And consequently, this is also why you have to average relative humidity and not absolute humidity, right? The relative humidity, you have again this exponential scaling in it. Okay, so that's sort of a little bit of a background. A second part that is interesting in Manabe's result is that they assume, right, you have basically a connection between the surface, so the surface would be the initial conditions for the entire column. But if you think about the real world, this is just two pictures. This one is over Switzerland. And you clearly see that the boundary layer here is decoupled from the overlying free troposphere. There is no connection in this situation. The same one is this, what looks a little bit like water is actually fog, so this is in the early morning. So this is again a case where the ground was rapidly cooling relative to the atmosphere, and you have a decoupling of the vertical structure. And so one question that we can ask is what actually controls the statistics when we have deep coupling versus when we have no deep coupling. And so I focus here a lot on the tropics, where basically it's deep convection that couples us throughout, sort of from the ground to the atmosphere. And the picture that we would sort of use is that the boundary layer is at any given moment tied to the surface, right? So they do not decouple. But the free troposphere is only controlled by whoever kind of brings mass into the free troposphere. And I have you here this little schematic, and the idea is that on average, maybe the tropical average temperature might be this. But basically, kind of when you have convection and you fill the free troposphere, the conditions are a little bit, you have a little bit above average temperatures, right? That is the nature of convection. It tends to happen at the highest end of the energy spectrum. So the average then is that the free troposphere is warmer than what you expect from the average surface temperature, and that automatically means you have a boundary layer inversion. Right, so it's a natural result of the thermodynamic propensity for convection to happen at the high end of SSTs. Okay, so in a geographic picture, right, this is taken from IPCC. Right, so the idea is, yeah, you would have the warm ocean, you have deep convection, you detrain here, and then you have the cold oceans, where you then have a very strong inversion layer, and you have clouds, maybe something akin to that on the picture to the right. And because the inversion layer or the inversion strength is very important for how much clouds you have. What you're really also interested in is now the temperature difference or the energy difference between here and here, right? Because that controls, in the end, how much inversion strength I have here. So in a schematic, as I said, if we sort of have local coupling everywhere, right, it means we can write the conditions here as function of what we have at the surface. We don't really would have a strong inversion. In reality, it looks more something like that we have some warm regions, some cold regions. They're coupled throughout the boundary layer, but the free tropospheric coupling happens primarily over the warm end. Now you can ask what happens if the gradient in the surface energy is increasing. Right, so one possibility could be that we still have this exchange here, but now we obviously have a stronger inversion layer here. The second thing what could happen is that actually the exchange also responds to the change in what we might call the evenness or the variance of the surface energy conditions. And one possibility is that what you might have is aggregation or contraction, that sort of only over a smaller fraction of the domain you now have exchange, and it could have impact on free tropospheric humidity, for example. So this is what we want to explore, and the question is, do we see evidence for a decoupling between these two possibilities? So we have the mean, and the other one, let's say the variance or the gradient, sort of in a PDF type sense, right? And what we know from climate models, and this is why people did not pay too much attention, is the dominant mode is the mean. You know, we're used to writing all the climate states. Climate change is usually expressed as function of global mean surface temperature. Right? And that basically simply means that there is no second degree of freedom here that you need to take into account. So the argument is, or the question is, can we observe that there would be a change up here that is not driven by the mean change in the surface condition? And the way how I went about that, I look into the tropics, and what I'm doing is simply I'm taking the tropical average temperature profile from the ground up to the tropopause. And I average the boundary layer conditions. And you can do that for the ocean. You can also add land. It adds a little bit complexity. But let's just think about it for the ocean for the moment. And the point then is whenever sort of the surface conditions are warmer, you would expect that the free troposphere is also warming up. Based on the moist adiabat, it should be actually larger, higher up than at the surface. This is a well-established moist adiabatic lapse rate process. Now let's do this correlation, and then let's take this signal out. Okay? So we take the residual from that signal, and this is what it looks like. So you have here the time is from 2000. Sorry, this one shifted. It should be over here to 2019. I've took this period because this is the period that Cirrus EBAF gives us data. And I've simply taken sort of ECMWF, sort of boundary layer, average temperature related to the whole profile correlated. At each level, I have a regression coefficient that looks then the profile like a moist adiabat. I take that out, and what you're left with is these variations. So the interpretation is here. It means that compared to the average boundary layer state, the free troposphere is anomalously warm. So we don't know what the mean is doing here. Right? We've taken that out, but it means that basically this kind of the warm end is anomalously high or warm compared to the mean. So this is a state where we have a stronger inversion strength, and then you see here a weaker strength. And so it's very clear, right? This is not noise. This is a very, very strong signal. The question is, can we relate it to the surface condition? So I look at the ocean surface temperatures, and there the problem is always things move around in space. And we cannot look at any one given location if things are moving around sort of where the convection is. So the simple trick is we simply bin all the sea surface temperatures from cold to warm. That's a very sort of a poor man's approach to basically track the convection, because the assumption is that the convection will stay in the warmest percentile, no matter where that warmest percentile is. And so what we end up then, is a percentile figure where this is the cold end and this is the warm end. And we simply would then have a mean profile, so the mean temperature here is higher than here. We deseasonalize that as we do sort of typically for each percentile then. And then I'm taking out the mean of each month. And what we're left with is changes in the shape of the probability density distribution. So we're not seeing anymore whether it's on average warm or cold now, but what we're seeing is whether the warmest part is now the same sort of difference to the mean as it would always be, or in this case, that means it is still warmer, but relative to the typical difference between the warmest and the average, it is cold. And that, of course, because the mean is taken out, has to be balanced by the cold end is now anomalously warm. So this state here is a more even sea surface temperature distribution, right? So they become more equal. On the other hand, when we have this situation, that means now the warm regions are anomalously warm. So that is a more uneven SST distribution. And we can line these two figures up, and you see that it is doing exactly what we expect. Namely that these cases, for example, here, when the free troposphere is anomalously warm, this is a state when the highest SSTs are anomalously warm. And vice versa, when it is cold there, the free troposphere is also anomalously cold relative to its usual state to the boundary layer. So we have established that there is indeed this sort of oscillation, or it's a second mode, that is only dependent on the shape of the PDF. It's not the mean. As I said, the mean is the one that we understand well. This is telling us that the shape of the SST distribution is really important as well. So why is that relevant? So for example, we can look at shortwave cloud radiative effect again. And in a nutshell, the black line here is the series EBAF data. The green and the blue lines are regressions that I do against the average surface temperature, and a multiple linear regression where I also take an indicator of sort of how even my SSTs are. I call that here SST sharp, or we've used different sort of metrics. In the end, they're all very highly correlated. And the point is, if you take these two modes together, you get a much better, that's the blue one, fit with the observations. And they explain over sort of the series EBAF period about equal amount of variance. So over the observed period, they have roughly the same significance. I'll skip that for time. Now the first question that I want to address next is actually, sorry about, much of this variance is related to El-Nino. And that sort of poses the question, what exactly is El-Nino doing here? And the question is, why is actually El-Nino warm? And that seems like a very naive question. Everybody knows why El-Nino is warm. It's sort of these cold upwelling regions, right? The upwelling breaks down, so the warm waters in the Kelvin wave goes east, and you have this warming. So it would be an adiabatic redistribution of SSTs, whereby basically you simply would have a larger fractional area of the warm SSTs. They're not necessarily warming up, but it's just sort of the kind of the area, volume that you typically have over the Western Pacific is now more distributed over the ocean surface. So the warming then is, is actually, I think I lost the slide. Anyway, is right, so that the pattern looks like this, and if you just look, this is average, this is El-Nino. Hard to see. If you do the difference, you have exactly this situation. So this Eastern Pacific region is kind of very warm, similar kind of for the upwelling regions here off the coast of South America. So these are regions that are normally cold. So this would be exactly the situation where you change the shape now such that the cold end gets warm, but it does not necessarily mean that the warm end would get warm. This is interesting because we just said that the cold end is not necessarily coupling very deep. But if you look at, this is 300 millibar temperature anomaly, you see this El-Nino signal, so the red or the pink phases are El-Nino. You see that sort of in the 97, 98 El-Nino, it got about 1.5 kelvins warmer there. And that is a bit hard to explain if sort of in the cold regions, which are now less cold, but they're not necessarily warmer than the average or sort of the warm waters what you had before. So how do you generate such a strong signal? It's obviously the warmest waters must also warm. And this figure shows that, again, I'm just zooming in the 97 El-Nino. And what you see, this is deseasonalized profile, again, tropical average temperature. And what you see, this is the onset of El-Nino. The boundary layer gets warm, and this is largely because the cold regions are warming up. But the free troposphere is not responding very strongly. Instead, it kicks in really in the decay phase of El-Nino. Now, people have realized that before, but what has not been really clear to me, at least, is why is it that you see in the mean it's not different here from here? So why is it suddenly kicking in here? And again, if you look at SSTs, you see exactly that. This is the cold end. The beginning of El-Nino is sort of in the cold percentiles, so it's anomalously warm. But then this warming anomaly propagates, and in the end, in the decay phase, actually it is the highest SSTs that are anomalously warm. And that is not so easy to explain how thermodynamically you sort of can produce a warming of the warmest. So Alison Hagikian, a student working with me and Laura Splone, they looked into that. And what she did is, again, this is the time series. This is cold to warm. And she looked at the heat budget of the ocean mixed layer. And we know the exchange fluxes. And so what you see is that, here. In the cold end, what you actually have there is a warming. But this warming is followed with a strong cooling from surface fluxes. So that means the surface fluxes are these orange ones here, so they are negative feedback. What does that mean is, as temperatures go up, you start having more evaporation. That's probably all our intuitive expectation. The energy must come from somewhere, and obviously in this case it's the subsurface process, which is exactly that, this Kelvin wave, and so we're not having the upwelling anymore. So this is kind of what we expect. It's a different story when we look at the warm end, where we have warming, but now the atmospheric arrow is actually positive. So that means in the warmest end, the atmosphere pumps energy into the ocean. It's not that the ocean somehow, is warming up because you bring in warm water and then you lose that heat. You can't bring in warm water to the warmest region that you already have. All right? So there's got to be a different process, and it's obviously it is the atmosphere. So one might think it's shortwave radiation or something like that. It's actually not. It turns out that the dominant process, right, of this thing is the latent heat flux change. So again, this is the cold end. We see an increase in the latent heat flux with warming as expected. And at the warm end, we see a decrease of latent heat flux with warming. Okay? So if you think about the bulk equation for the evaporative formulation, it's proportional to a moisture deficit, and the wind speed also plays an important role. So if you look at the moisture deficit, this is this one, it actually doesn't do anything in the warm end. It does exactly what you expect on the cold end. Temperatures go up, the saturation vapor pressure at the surface is going up, the boundary layer is lagging behind, so you have a larger difference, and correspondingly you have an increased net flux into the boundary layer. This is not happening over the warm part. Instead, what you see, it's entirely driven by a decrease in the wind speed. And so the point is, this is very much driving this strong warming and is very much responsible for this second mode that we see related to El-Nino. Seems to be a mechanical aspect whereby obviously a rearrangement of the geographic distribution of convection might also have an impact on the typical wind speeds in the convergence zones, right? That's not very far-fetched, but it's something we're still working on. So we haven't worked out these in detail. So I explained to you kind of what happens over El-Nino, and I've made the case that we see these two modes. So let's go back to the global warming, this first figure that I showed you. This is another one. This is one of the first papers that made this case. Again, historical period. They look at the cloud feedback in their model if they use observed sea surface temperatures. And what they calculated here is over 30-year periods, the feedback. And what you see, it is time varying, and again, it's going strongly negative over the last sort of 4 decades or so. So this is the equivalent figure to what we then plotted here that I've already shown you. So if something happens here, and if you think in our two modes, that would now basically mean that maybe sort of this generally decrease in shortwave radiative feedback would be a general warming signal, right? We sort of generally think models with a warmer surface temperature, you have less low clouds. In order to produce this could be the second mode. Namely, if it's not only the mean, but we're also amplifying the difference between the warmest and the coldest. And lo and behold, this is actually what the model does. The black line is the GFDL AM4, also with observed sea surface temperatures. It's the global average shortwave radiative effect. And if I regress that against the average tropical surface temperature, I get this orange line here. And I regress it up to here. And then I continue using the average surface temperature to predict what would be the model result if it was only the response to the average temperature. Right? And that means we have global warming since then, so it would continue to rise. Instead, the model shows this decrease, and I said this is then if we add a second independent variable, which is a metric for the difference between sort of where you have convection and the average, then you can explain that very, very well. You see, this is not a small effect. This is half a watt that we're basically missing in this calculation. So the question is, what's going on? And is it real? I cannot answer you the question, is it real? And I know that quite a few people have put up a forced response mechanism, but I think the jury is still out why the coupled models that to some extent have these forcings in them are not showing that. So instead, I want to focus on exactly that, namely what different, or how different is a coupled model from a so-called AMIP simulation where we have prescribed sea surface temperature. So what I show you here in gray are the CMIP6 coupled atmospheric ocean GCM results. It's the mean temperature, and so I have a lot of models with a lot of realizations. So each line is one model and one ensemble. And I'm looking at also what they do in terms of this metric sort of warmest versus average sea surface temperature in the tropics. And that is what I have down here. The pink here, I've added then also the CMIP6 historical simulation. The gray is CMIP5 historical and RCP 8.5 simulation. So it's just a whole set of coupled simulations. And what you see then is the color is what you get when you run a model, an AMIP model with prescribed sea surface temperature, either from HADES or ERSST5 or the PCMDI. This is what they use for CMIP6. And the point is, first interesting, the mean is different, but also in terms of what they give us for the change in this metric for the evenness is exactly what we needed to understand why these models then have such a strong negative cloud radiative feedback, right? This is really very different from what these coupled models do. So if you plot that as a scatter plot, where I have on the x-axis the mean sea surface temperature trend, on the y-axis I have this trend, we call it here delta convective, the trend in that, what you see is generally, all these little points are 30 years intervals in many models and many realizations, many ensembles, different experiments, but they're all coupled, okay? And what you see, there is a general correlation of about 10%. So meaning a coupled model gives you a little bit of an amplification of the unevenness of sea surface temperature. But it's relatively modest compared to what you get when you use an HECM with prescribed sea surface temperatures over the last 40 years. So this is sort of 79 to present, the calculation. And you see, it's not completely out of the possible, but it's sort of a 1 in 1,000 event, more or less. What's even more disturbing, and that sort of, I'm interested also to learn from JPL, if I'm, instead of just focusing on sea surface temperature, I can also look at observed rainfall and try to determine what does rainfall tell me where convection happens. Right? So it's the same sea surface temperature, but rather than just saying I'm taking, say, the warmest 30% or so, I say I'm deliberately only tracking what are the SSTs where I have strong rainfall. If I do that, then I end up here, and this is combinations of different SST data sets. So the green is COBE, ERSST5, HEDI SST, PCMDI is red, with 2 different rainfall data sets. So one is GPCP, the other one is CMAP. And the point is, that is the same period as what this is an atmospheric model with prescribed SSTs. So you see, they are even more out of the norm of what the coupled GCM gives you. So that is very, I think, dramatic, because it's exactly the best observed period that we have, right? It's only over this period that we actually have satellite data, that we actually can make statistical statements about distributions and not just have a few single ground-based stations. So, as I said, particularly the 80s and 90s are pretty peculiar in what the observations tell us. This is very hard to confirm with observations, and it's boiling down how well do sort of these remote sensing observations of sort of a couple decades ago, how reliable are they, is something that I'm really interested to learn more about. But what we definitely can say is that ENSO confirms there are these 2 modes, and they're very, very impactful, as we have seen. And what we now kind of wonder is, what do we learn about the second mode, and how important, that's the question, is that for climate change? Right? Sort of, because models tend to put everything more or less on the first mode, on the change with the mean. So a related question then is, can we make a statement about the coupling between land and ocean? And there the idea is, again, that basically the free troposphere would be driven by whatever conditions we have in where we have deep convection. Now in the tropics, we know the Coriolis force is very weak, so the tropical atmosphere cannot sustain strong pressure gradients, and that is roughly equivalent to weak temperature gradient. This is also kind of known as the weak temperature gradient approximation. It doesn't say the gradient is 0, but it says it is weak. And that basically would mean you would establish a coupling between whatever happens here. You start filling the free troposphere with the conditions here, but the region over here and over here would know about that. All right, so it would be exactly this situation where we would now have coupling, but it's pretty far distant from each other. But because we have the weak temperature gradient, this is a strong coupling across large distances. And so the question then is, are conditions over land when you have convection, are they coupled to conditions over ocean when you have convection? So we looked at that problem, and my student Yi Shang, she calculated the mean subcloud moist static energy in the tropics, separated into land and ocean. And you get this picture here, and you see, they sort of both have a maximum, but they're not following each other very closely. And in particular, with the northern hemisphere, you have quite a substantial departure from the 2. If you restrict that then simply on asking what is a subcloud MSE in those regions where we have strong rainfall, so the convective domain, the picture looks very, very different. Now the land and the ocean are actually at almost the same level, and it is very flat throughout the tropics, which also tells you something about the lateral connection, the distance as you convect. You actually know it also not only in the zonal direction, but also in the meridional direction. And you see a very nice fall off now sharply kind of when you come into the exotropics, where the Coriolis force starts being more significant. So this is a really sharp shoulder here. There is something here that is very disturbing if you're concerned about heat stress, in particular over India, which is India is exactly sort of at the transition to the subtropics, and quite remarkably, it is exactly here where you see the land depart from what the ocean is doing. So, question, does that hold also on a given month? Right, so the previous figure was a time mean. This is the mean annual cycle. All what we do is we take basically this profile for each month. We subtract what happens sort of around the equator, and we plot the anomaly thereof. And the picture that you get is like this. So if we split between convective and non-convective domain, it looks like this. So we have sort of, this is more aching sort of the meandering of the ITCZ or so, or the warmest regions. And you have a relatively strong decay with latitude to both sides of the MSE. Conversely, in the convective part, you see it's very, very homogeneous and sort of in latitude. And you see that also over the mean annual cycle, it's not varying very strongly. So it's more or less staying throughout the year at roughly the same value. There is almost no annual cycle in the subcloud MSE. But if you do a tropical average surface temperature, it actually does have, it's actually a semi-annual cycle. And so you're not seeing that in the maximum kind of MSEs that we have here. Good. It also holds past and future, at least in models. So this is the calculation as before, but now we have the last glacial maximum climate simulation. This is the present, and this is the RTP 8.5 scenario. So it holds in all climates. And that now allows us to couple basically the high energy conditions over land and ocean, right? We can't make a statement about what happens when you're not at the convective threshold. There, land and ocean can completely decouple. There is no statement about that. But you can make a statement about the maximum. And this is obviously interesting if you're interested in, for example, humid heat, which is basically the question not only temperature, but also kind of whether you can actually evaporate or transpirate, right? And the metric that people like here is the so-called wet bulb temperature. And the wet bulb temperature, and that's kind of the nice thing, that's why we like it, is basically equivalent to monostatic energy at sea level. And so it simply says that you can equate these two things, and as at the wet bulb temperature, it's basically, right, if you're in the desert, the temperature can be very high, you can still evaporate. So your body has not a problem getting rid of the heat. And so you can convert that back into basically a temperature, and that's what the wet bulb temperature is. So it's just a different metric. And so that means that's the same thing now as MSE, and you see this wet bulb temperature has a maximum where the MSE is a maximum, and the MSE has a maximum where we have deep convective coupling, and that means the maximum regions should be basically coupled between the land and the ocean. Okay, and that is now very nice. What Yishang showed here is on the x-axis you have the tropical mean warming following a climate change. So this is a 4 Kelvin warming. I think it's the RCP 8.5 scenario, but it basically holds with whatever scenario you look at. And the red is simply the temperature maxima that you observe in 4 different regions. Okay? And so the spread here is between different models. And so you have sort of a different amplification. But what you see is that if you look here, this is 4 Kelvin, and the surface temperature here, the maxima scale roughly like 8 Kelvin. So it's about a factor 2 more. But that differs substantially between different regions. And the first thing that you should notice here, actually this, you have a lot of convection here. So this is a region where you have a lot of coupling at any given moment. Here, the departure is not so dramatic between what the maximum temperature and the maximum, the average temperature is doing. And that would be sort of giving us the first hint that humidity does play a role. So when your humidity is very high, then the humidity difference cannot do anything, and basically the wet bulb temperature is then equal to the actual temperature. And so if we then calculate as at the wet bulb temperature maxima, you see this is the one-to-one line, and now this is true that the maximum wet bulb temperature in this domain at any given time is basically correlated one-to-one with the average temperature of the ocean at that moment. And that is a very powerful statement because it allows you now to relate the maximum to something that you know of the mean. And generally, we trust the mean more than the maximum. And the maxima, right, you could think, well, maybe, these are very different regions, and maybe I need a very high-resolution regional model to capture all the subtleties of the meteorology in these regions. And the point here that we make is, well, for a specific event, yes, you need to do that. But if you want to sort of have a rough guess what sort of the maximum could be that could happen, then you can operate with the scaling, right? And that is pretty good news. Before I finish, what I want to emphasize here then is this is a climate model result. And what I said before was exactly the climate model plays on the first mode, on the mean. A coupled model don't have a strong signal in this second mode. And of course, you can see that if this second mode was for climate change important, then it would look different here. Because that would also mean you would have a decoupling of the extrema from the mean of the tropical temperatures. Good. With that, I come to my conclusions. I've made the case that we can think of what people also call the pattern effect, that to some extent we can just think of it as a thermodynamic or radiative thermodynamic mode of climate, which simply says it's not sufficient to only know the average surface temperature, but you also need to have information about the distribution of subcloud MSE, because that is controlling kind of what you then have in the free troposphere. So there are basically 2 degrees of freedom. What we observe robustly is related to El-Nino. Right, so that's sort of the last 20 years. We really can see what's happening, and we trust that. In the historical SSTs, there is a strong role for this second mode, particularly over the last 4 decades. But it is a bit hard to confirm that with observations where things have been really like that. So this is a model result. You use the SST that you have, and then you run the model, and you hope that your SSTs are perfect. Right? So if the SST would have a little bit of bias somewhere, then the result would be different. What we then also said, this allows us to make a statement about the coupling of land and ocean. And the nice thing is this always holds no matter which mode plays a role. But the question then is the scaling as we go forward, right? Which of the 2 modes should we concern most? This allows us to establish a theoretical limit or ceiling for the heat stress over land. And that's that coupled models go with the mean mode. And the question is, how much or how important is the second mode for global warming? And with that, I thank you very much for your attention, and I'm looking forward to questions. So, I forgot to say, I would also like to take the opportunity to thank my group. Over the years, it's always been a great pleasure working with them. I only had the chance to highlight the work of Sri, Levi Silva, Yi Shang, and Alison Hogikian, but it's been a great pleasure with working with all of them, and that's kind of why I like doing my job. Thank you very much.
So we have time for questions. There's a question on
There's like 3 questions on chat.
Do you want, on the chat? Do you want to ask them if they want to ask a question? Do we need a mic, by the way?
Evan, Hani, and Mark, would you like to ask a question? Or Evan first?
So we are asking people online if they want to ask the questions directly. So we have 3 questions. One is from Evan Fishbein, one from Anna Takahashi, and one from Mark Richardson. So let's start with Evan. Do you want to pose your question? Evan Fishbein? Okay. Do you want me to ask the question? So Evan is asking, how are the states separated in the convective and non-convective mode? Or in convective, non-convective?
So just technically how I separate it.
Yes.
So Ages ago, we started basically with just looking at precipitation, and you could sort of have a precipitation threshold to separate sort of convective from non-convective precipitation. It turns out that it's not overly sensitive. So one way to go would be simply you weight the area of a given cell based on how much precipitation you have there. That's sort of a precip-weighted sea surface temperature. In order to do that, you already need to know additional information about the rainfall, right? And so the next step then was, can I further simplify that and simply say, I only need to look at sea surface temperature. And there it turned out that a metric like I'm taking, say, the warmest 30% and subtract that from the average, that gives me a delta. That works also quite well. So there's different ways how we can do that. You could also look just at variance. So just calculate the mean and the variance. What you would find is also, again, that the variance is highly correlated. So the details in the end, how you calculate it is not overly sensitive. What's interesting, what we found is that to some extent, this means that if you think about the shape of the PDF, is that it's not doing highly esoteric things. And so it really means that the leading mode is simply basically a flattening of the gradient between warm and cold. And it's not doing strange spikes at certain percentiles. Right? That would be much harder to capture. So the leading order, as I said, you can think of sort of a mean change and a change in sort of how steep the gradient is. So.
Thank you. So do we have questions in the room? Matt, and then we'll go back to the online.
Is this on? Yeah.
Yep.
So I followed your argument about how the surface latent heat fluxes modify that PDF, and wind speed seemed to be important there. Maybe you mentioned it, but it wasn't clear to me why the wind speed changes. Do you have any thoughts on that?
Yeah, I have some thoughts, but I prefer not to speculate too much in the sense that we have not analyzed it in great detail. So what seems to happen is that the geometric, right, sort of the arrangement of where your convection is, right, is in an El-Nino situation, it's much more zonally symmetric, it's spread out, and it is conceivable, but as I said, this is speculation, that simply this arrangement means that you need to, the convergence that you need to generate could be a little bit weaker. Sort of if you would have all the convection in one spot, then you need to transport all that mass across the whole domain, and so your wind speed would be much larger than when you go to a more ergodic state where you just distribute your convection everywhere. And I suspect that it hinges on that. But as I said, we haven't seen it yet, or sort of not been able to prove it. But I think for me, the important thing was simply is to say that we assume that the SSTs are the way that they are. Warm is warmer than cold. But we don't really have a good scaling argument for how much warmer sort of the convecting regions should be. And so I thought, kind of for me, the interesting thing is it's really not only thermodynamics, but there also seems to be this wind component in it, right? And if maybe sort of the mean climatology of the planet would be different, we might have a difference in sort of this amplification, and that would mean the mean inversion layer strength of the tropics would be different, and that would mean we would have a different mean cloudiness, right? So yeah.
So while making that argument, would you mind going back to that figure that has the map, the basic sort of SST map between El-Nino and mean? And so just to be clear, you have the map? Yeah, right now. So just to be clear, when you're talking about the warmer regions where you have the wind speed going down by 2%, where are those warmer regions there?
So yeah, it's roughly it is this region here.
Okay.
But it also turned out to be actually quite a nightmare of bringing things that are in the PDF. So when we saw it so obvious, bringing it back to the map, because it's a moving target, and you basically sort of have just a density, right? Sort of not all these points map exactly on the same percentile and vice versa. Right. And it is, again, what one has to bear in mind, it's a percentile average, right? So we have equal SST, but we may have different wind speeds, so there are different locations, and so it was a little bit hard to sort of have a very convincing map. But the way to think about it is largely is to think around sort of this region here. Okay. And you see this, you know, the warming here is really not strong. And one easily overlooks that, but it is sort of where then the maximum is. And we typically tend to look here, where the delta SST is very large, but even if you warm it up by 4 Kelvin, you're still not in the maximum percentile.
Okay. To follow on then, it seems from your argument that about the wind speeds that where the PDF is, where the temperatures are changing matters. And at the very end of your talk, you related this to the pattern effect. I guess I'm wondering if you could comment about, is it really just the PDF, or is it also the location of where those temperatures are changing?
I said a lot of sort of my motivation here is that if you, that you have the rest of the community largely speaks of that as the pattern effect. And if you think about a pattern, then that it sort of suggests that every pattern could have a different response. After you go sort of more towards this local perspective, that you think kind of I do a derivative to whatever location I have, and then the response to the climate would be in every location you would have a different sensitivity, and that would mean you have no chance of sort of getting sort of an overall picture, because whether you know how you align this, do you do it as a checkerboard, or you do put all warm in one part of the domain and all, and so it would all sort of be very, very different. And I think the argument here is that probably you can simplify that, and basically really just asking how do these patterns project onto these SST percentiles, right? That sort of generally you get one type of response when you're in the cold end, and you get one type of response when you're in the warm end. It doesn't matter so much where that is. It's just that because the climate is very sort of a quasi-stationary structure, you know, you can equivalently emphasize the Western Pacific. I have deliberately not done that because we could have a different planet or a different climate where it's not located in the Western Pacific, but the principle would still hold, right? Yep.
All right, so we go back online. So Annie, do you want to ask your question?
Hi, thank you very much. Can you hear me?
Yes.
Okay, thanks. It was really interesting talk, and you actually already replied my question, which was very similar to Ivan's question I had. First, I thought convective versus non-convective, it was like a different stage of deep convection, you know, the area is growing and like dissipating. But you mentioned it's more like based on the precipitation, right?
Say again, what was the question? The last part I did not understand.
Oh, I think the separation between convective and non-convective, it's based on the more precipitation side, not the stage of deep convection. Like a growing versus dissipating stage? Or is that something related to that?
Sorry, I have a hearing problem, and I struggle. Jean,
Yeah,
can you?
So I can read, I mean, do you want me to read the question on the chat? Maybe that's a better one? So the question is, when comparing the differences between land and ocean, do you compare the same or similar stages, growing, mature, or dissipating of convection, or are they all mixed? So again, it goes back to the same question.
So you're really asking me now about the meteorology of what happens with deep convection. We did not look into that.
Okay, all right.
We really only looked at the surface energy conditions. And our take was really that in the end, right, when you read the literature, convection is different over land and ocean. And so we were very surprised, actually, to find that when we just look at the subcloud MSE, that it works really well. Because the literature is full of emphasizing that it's two different beasts over land and ocean. But from an energetic perspective, obviously, this seems to be less the case. But we did not look specifically at these details.
Okay, thank you so much.
Thank you.
Thank you. Any other questions online? I know, Mark, you have 2 questions online, but I was wondering if there's a question here. Person? No. So Mark, why don't you ask the first question and see if we have enough time for the second question?
Hey, Stefan. Great talk. So you showed an example of the 97-98 El-Nino. I wondered if the effects that you were reporting would depend on. So we currently think there are maybe two flavors of El-Nino, Eastern and Central, and also its pattern may change with warming. How does that matter, I guess is my question, or does it matter?
Yeah, we did not look at different flavors of El Nino other than basically thinking they can be stronger or they can be weaker. And the basic argument was simply the effect should be more visible the stronger El Nino is. And this is kind of why I showed you this case study of the 97-98. Over the last 20 years, I think I would not lean out that there have not been statistically enough El Ninos that one could make a very strong statement about that. Does that answer the question? Yes, so answer is I can't tell you.
Go ahead for the
Okay,
second
that's
question, Mark.
cool. I would say that maybe inside the large ensembles, you could play games and see whether you would get sample sizes from that. But not too important. My next question was about, you showed the AMIP versus CMIP. These two graphs. On top you had the mean, and on the bottom you had this gradient or SST sharp thing.
Yep.
Some of the CMIP5 models had a change in the gradient in the future that's similar to what was seen in AMIP.
Yeah,
Do those models show any different behavior that you can link to? Is it something that causes the change, or does it change the feedbacks, or what?
Does it change which maps?
There are some models which show the change in the gradient in the future in CMIP5. Others do not. Is there something that distinguishes those two, and can we read anything into it?
I'm not sure I can comment on that. I mean, the big question is, if I can take your question a little bit, is in the end, what is the warming pattern generally, right, over the Pacific, which is yet another question in itself. So yeah, sort of the models that generally show this sort of El Nino-like warming pattern, and it's basically boiling down to a very similar thing that the AMIP simulations sort of have a more La Nina-like warming structure in the observations. But yeah, I did not look sort of further into what models do, but I think to me maybe the most important thing is that coupled models don't like, if I summarize that, playing on that second mode. Coupled models have this very, very uniform, everything goes with the mean. And this is why decades of climate science could basically just focus on the mean, and you can plot everything as function of mean temperature. And that is simply because the models are not projecting strongly on that second mode.
But the AMIP models do.
Yeah, but that's with prescribed SSTs, right?
So we trust them more, right?
It really all boils down, what are these prescribed SSTs really, what do they mean? And people generally trust them, but it's also true that when you start looking at it closer, there are differences between different products. And one thing that I'm still worried a little bit is a lot of the information comes from thermal satellite imagery, which is affected by convection. Sort of cloud contamination. Could there be, it's exactly those regions where you want to know the temperature. So if there have been trends a bit in how we can detect or how well we can screen our clouds, would that have an impact? I don't know. Yeah.
Right, yeah. But it could be, yeah. I mean, there's good reasons why the AMIP runs could work and the coupled ones couldn't. That could be related, for example, not to the ocean, but to the atmosphere. The atmospheric model, there may be biases that the atmospheric model creates that are completely irrelevant if you're not coupled. And in that sense, that could be the reason why it wouldn't work in a coupled system. I think this is a wonderful time to thank you again, Stefan, for the presentation. I know many of you will meet with him during these 2 days. But if you really want to meet with Stefan and you're not on the agenda and you urgently want to be on the agenda, just let me know. All right, thank you. Okay, Brian, I think we have this room available apparently.
Changed it.
So we don't have to change it.
Yeah.